Hi, and welcome to another online meeting for MTH129. So discrete math. So this week we're looking at probability distributions. Um, so which helps with the last few questions on the online assignment. Um, so I'm just going to go through some of the tutorial exercises that I did with the internal students. Um, and one thing I want to try to do to begin with, try to make it a bit more concrete. So um, what really throws people is that um, essentially probability distributions are just a way of spitting out lots of numbers, and people from school, high school, maybe even primary school, from FR, sort of remember ideas like average and maybe standard deviation, maybe variance, that sort of idea. Um, and it doesn't seem to marry up with some of the things we have for the language we use for the probability distribution. So, for example, EX um, is the way I write down the average. It stands for expected value. Um, the reason why I use these some funny terms is because I would like to better talk about the expected value for an average or things like that, which we fortunately don't go that far in this subject. But um, it just also, even though it's an average, yeah, well, it's a different node, it's not a problem. The formula doesn't quite seem to marry with what we know. So I always want to try to make it a little bit more concrete, um, and then go back to the doing it quickly. So here we've got a random variable. So random variable means you've got um, um, some variable, so the result of which you don't know yet. It will be some sort of number, and the not what number it actually corresponds to depends upon some random event. So this could be rolling a four-sided dice, for example, or it could be rolling a six-sided dice, which has different only numbers 1 to 4 on various of them. So I got the numbers. So 0, 1, 2, 3, 0, 1, 2, 4 even. Um, and we know the probability of getting each of these numbers. So a probability distribution really is just a list of all the values and the probability that you can get for them. So let's make it concrete. So if we have, 10 numbers. Suppose we had 10 numbers. On average, how many would you expect to get? Well, we expect 0.1 or 10% of the time we get a 0. So if we had 10 numbers, we'd expect one of them, I should do that. We expect one of them to be a 0. Well, let's write them down the bottom here with a 0. We would expect 0.4 or 4 of them to be 1. So 1, 1, 1, 1. We expect 0.3 or 3 of them to be a 2. So 2, 2, 2. And we expect 2 of them to be a 4. And it's a distribution, so that's what we expect on average. If you picked a bigger number, that would be more likely, but that's sort of just theoretical. That's okay. So you got a bunch of numbers here. So in particular, we have actual 10 physical numbers here, and so we can do various things with these 10 numbers directly. I want to get a sense for it all. So how do you work out the probability that x is greater than 1? And so um, the concrete way of doing it, just to show you how it matches up to the rest of the theory in case that helps people, is that x is greater than 1 means, well, if you look at the numbers, all of those numbers there, so the 2's and the 4's, are greater than 1. If you counted them, there's 5 of those numbers. So the concrete fashion would suggest there's 5 out of the 10 numbers we want to consider. So the number of ways of getting our particular event divided by the total number of ways we want to consider it would be our probability. So that's the concrete way. Just want to show you how it matches in concrete terms. I can count 5 out of the 10. The way to do it without having to resort to making up numbers would be, again, it's still the same numbers. 2 and 4 are the only ones that are greater than 1. And So therefore, the probability. So therefore, what we can do is the alternate way is to say, look, probably x is greater than 1. Well, that's either x is 2 or x is 4. They're the only real options. And because these you can't get 2 and a 4 together, it just becomes a plus. And the probability x equals 2 we can just read off is that 0.3. And the probability of 4 is 0.2. And you add them up, you get a half, 0.5, which is the same as saying 5/10. They're all exactly the same. So certainly the latter approach is how I'd encourage you to do it, but I just want to help you see it concretely. And this might really help when we start thinking of B. So we'll do it concretely first. That might help people. So this vertical line I'd read as the word given. So what's the probability x is greater than 1 if we know, or given, x is less than 4? So basically what we're considering is we've got 10 numbers here, but we're going, look, we've got 10 positive numbers, but we know that x is less than 4. So we really only care about just the numbers less than 4. If you count them, you got 1, 2, 3, 5, 8. So you got 8 possible numbers. So there are really only 8 numbers we want to consider, and you can just see them. So if you know those 8 numbers, what's the probability, or how many of those numbers essentially satisfy x greater than 1? And well, it's just only these 3 2's here. They're the only ones that satisfy x is greater than 1. And so 3 out of the 8 options we want to consider really satisfy that condition. So the probability that x is greater than 1 given x is less than 4 is 3 of the numbers out of the 8 numbers we have. And that would be the answer. That's just a concrete way of doing it. And so I really want to show you that this is a conditional probability. Essentially, it's like all probabilities, it's the number of ways of getting the event we want, x greater than 1, divided by the total number of ways we want to consider it. And there are 8 different ways we want to consider that possibility. And that really comes from the condition at the bottom. So how would you work it out without having to resort to making up lots of numbers? So this is the more direct approach. So you can do it the same sort of way, just looking at stuff. You can go, well, in the blue area, I know I've got point. So the other way to write it down, just by numbers, it's so I've got 0.1 plus 0.4 plus 0.3. So they're my 3 different cases. So I'm in that category. So I'm in one of these 3 different cells. I know in one of those. That's the total. That's really all of one areas I'm focusing on. And then I want to know if I'm in one of these 3 cells, I would like to know the probability of getting x greater than 1. So the only way of getting x greater than 1 and being in those 3 cells is this one here. So there's only a 0.3 of the time we'll get into there, but divided by the total number of ways of getting into those categories. That would be also a way of getting the same thing. And that sort of approach that really matches up to this 3/8 idea. And if you add them, if you do them arithmetic, you get the same answer. If you like formulas, to try to remember this approach using formulas, the probability of one event given another event is the probability of doing both at the same time, so A and B, divided by the probability of the condition, probability of B. Okay, you all still there, Dylan? You just seem to have popped up lots of times. Maybe. I'll just wait for you to resolve your identity crisis there. Sorry. Okay, okay, awesome. Um, as I was just saying, the general way of doing conditional probability is to say the probability of A given B is the probability of both divided by the probability of just the second one. So in this particular case, the probability of A given B, well, A is the condition x greater than 1, B is the condition x is less than 4. So the only numbers that are both greater than 1 and less than 4 is just 2. So the probability to get in that is the 0.3. That's the 0.3 on the top. And the probability of B would be probably x is less than 4, and that's the 0.1 and the 0.4 and the 0.3 add them up. And you can see that's effectively the formula I've used down the bottom here. I've just done it implicitly rather than explicitly as I've written it down, but it's the same thing, of course. So that's the idea of normal probability and a conditional one, and the conditional ones normally the ones that throw open more than anything else. Next question here is the expected value, which is just another way of saying find the average. That's what it really is. So the way to work out averages, if you had a bunch of normal numbers, so if you got our 10 normal numbers here, how would you work out the average for these 10 numbers? Like, remember thinking about what you used to do at school, perhaps? How do you work out the average of those 10 numbers? Add them up. So you add them up, you get, which we can do quickly. So you get 4 plus 6 is 10 plus 8, which would be 18. So there's 18 of, if you add up all of them, and then divide by how many there are, which is 10, as you say, which gives you an answer of 1.8. That's how you used to do it. So what I want to do is want to try to extend that sort of idea to using probability distribution. So I'll show you how the sort of formula matches up. So let's just clear some space here. So, basically, we reckon it was 1.8, but let's just sort of show you. So the way we sort of count how many numbers, if you want to add up all these numbers, how we want to do it, well, we've got one lot of 0, and that's pretty easy to add up. It's just nothing. We've got 4 lots of 1. So you add up all these 4 ones, you get 4, but that's just another way of saying 4 times 1. And if you add up these 3 2s, it's just another way of saying 3 times by 2. And if you're adding up the 4s, there'll be 2 lots of the 4. And essentially, if you add up all the numbers, you add them all up, and then you want to divide by 10. And so we want to divide the 1 by 10, the 4 by 10, 3 by 10, and the 2 by 10. That would be the average. So the way we work at average is add them all up, and that's just a shorthand way of doing it, particularly when you've got lots of repeats. That's how you do averages when you've got lots of repeats, and we divide by how many there are. But if you notice what we have here, when we write that down, this 1 over 10 can be written as 0.1 times by 0, and the 0.4 can be written as 0.4 times by 1. And the 3/10 here can be written as 0.3 times by 2, and the 2 over 10 can be written as 0.2 times by 4. So if you notice, all these point numbers here are just the corresponding probability. So that suggests that the way to work out averages in general really is to sum over all the different values. So that sigma means sum. So summing over all the different values of the values we want to have times by the probability of getting them. So maybe for short, x, so I've actually written the other way around. So probability, so 0.1, 0.4, 0.3, whatever, multiply it, so the value, 0, 1, 2, 3, 0, 1, 2, 4, 0, 1, 2, 4, multiplied by the corresponding probability you get, and then add them all up. So that's sort of the suggested formula, how you work out what the average value of something is. So if you multiply it all, so 0.1 times 0 is nothing, 0.4 times 1 is 0.4, 0.3 times 0.2 is 0.6, and 0.2 times 4 is 0.8. And if you add up all those numbers, you get the 1.8, which shows the concrete way and the quicker way, using probability distribution directly, give you the same answer, which is always nice, of course. But it shows you how this formula comes about. And again, it's this formula here that I encourage you to use. So the expected value is the sum of the values times by the probability of getting that particular value. And you can do the same sort of concept to work out other sort of expected values too. So the average we know, average is some sort of middle position. It's also useful when dealing with distributions, not how spread they are. And a good way of measuring that is called the variance. It's really the expected squared deviation is the one fancy way of saying it. In practice, the way to sort of estimate it, and this is sort of the formula, would be to work out the average value of x squared and then subtract off the the mean value squared, or average value squared. So that's sort of a working formula. So this is the calculation formula for variance. And just linking what we've done, this ex squared here is just the average we worked out a second ago. And so sometimes I'll use the word mu for ex. Mu is just is the Greek letter for m. M stands for mean, which is just another word for average. But just linking what we've gone. So the way to work out the variance, then you have to work at the average first, which we know it's 1.8, and you have to work out what ex squared is. So instead of doing it the concrete way, I'll just use the probabilities way. So essentially, the way to work out the expected value for anything is to sum over all the different values, and because it's probably distribution x, to be summing over all the different x values, sum the actual value you want to have itself. So we're looking at expected value for x squared, so it's the x squared's values, times by the probability of getting that. So let's write a few down and I'll talk about probability then. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 4 squared is 16. So if you get a 0, that's happened because little x is 0. And if x squared is 4, it's because x is 2. So it really is just x squared times by the probability of getting the little x value. So what that looks like then is each of these values here multiplied by the matching probability. So to be the first value, 0 times by the probability of getting 0 to begin with, plus 1 times by the probability of getting that, so 0.4, so you get those more often than not, or more often than zeros at least. 4 times by 0.3 plus 16 times by 0.2. And then we add all those up. So how about get you to practice your calculator skills? Can you do that sum? So, and type it in. If you don't have a calculator handy, you can just press N. It's okay, but it'd be good to try to have a practice. And again, if you're watching this recording afterwards, So I know not everyone watches it live. I'd encourage you to pull out your calculator and just try practicing it. It's a good idea, because these are sort of skills you need to be able to do for an assignment or exam. Okay, so 4.8. Thank you. So that's the expected value, the average value of the x squareds, effectively. And so the variance then would be this number, so 4.8, minus the average value, 1.8 squared. And if you type that in your calculator, what do you get? Yep, thanks. So 1.56, that would be the variance. And it's a measure of spread. So commonly, people talk about the standard deviation. Do you know how to work out the standard deviation? So, yeah, question mark if you don't know. That's okay. Yep. So the standard deviation is the square root of the variance. And so that would be the square root of 1.56, which is about 1.25 to 2 decimal places. So the variance is the average of the squared deviation, and so if you ever had units to them all, so if these were meters, so this is all different meters, and the units for variance would be meters squared, and the standard deviation has the right unit, so it has directly comparable. So if x was number of meters that you could throw something, so you can do 0, 1, 2, or 4 meters, whatever it might be, then standard deviation would be measured in meters, and it's a measure of how spread out it is. So it's called the root mean squared, essentially, is other sort of terms for what it corresponds to. What it means, so the best way of using standard deviation is to compare, really. If you've got the standard, if you've got two different distributions side by side, if you know one standard deviation is bigger than the other one, you know it's more spread out. And you go, well, so you go, what does standard deviation of 1 correspond to? And I'll try to explain in a second. But what does a length of 1 meter correspond to? Well, it corresponds to the length of a ruler that's sitting in Paris somewhere. Well, it used to. It corresponds to a fraction of the. It corresponds to how far light travels in a. Was it 1/3 times 10 to the 8 seconds? I think it is how it's defined nowadays. So measurements are often defined a bit arbitrarily just to make them convenient for comparison. So that's what meters really are. So 1 meter is just a useful comparison and value. And so standard deviation of 1 is useful for that sort of purpose as well. So why is that particular value for standard deviation? The number of standard deviations away from the average has some nice properties. So for example, if you've got if you combine distributions together, and that's not very clear how you do that, but if you combine several distributions together multiple times, then the number of standard deviations away from the mean tends to have a normal distribution, which is something else. And so in particular, 95% of the time you have within 2 standard deviations away from the mean. So it has quite strong meanings, which is why it's people are quite fond of it. But some of that's getting beyond what we're doing in this subject. But I guess for our purposes, standard deviation is just a way of comparing spreads for different things. So talking about that number of standard deviations away from the mean, that's called the standardized value. So Z, or a Z-score, or a standardized value, is for any value at all, you basically subtract off the mean, which is EX, and then divide by the standard deviation. So, and what this corresponds to is the number of standard deviations away from the mean. So in this case, if I picked on 2, 2 would be, if you subtract it from 1.8, it gives you 0.2 above the mean. So that's the deviation away from the mean. And you go, well, how many standard deviations is that? So if we divide by the standard deviation, so divided by that by 1.25 would tell you how many standard deviations that is. And so you're getting about 0.16. So the value of 2 is a small amount above, so it's not many standard deviations above the mean. So, and values of, say, beyond 2 or minus 2 don't happen very often, for example. So they happen about 85% of the time, either side, or one, so both sides together. So there's more to some of that sort of stuff, but nevertheless, some things that are important is talking about distribution, being able to do probabilities, being able to work at the average, being able to work at the spread, and being able to do some things with them. And that's sort of what we're focusing on this subject. So you can tell there's more to it than what I'm presenting, and depending on what you want to do, sometimes you need to do those various things as well. And so sometimes you generate a probability distribution in real life, like you're going, look, I'm designing a web page, and I'm just trying to work out, if I cache things, where do people actually go more commonly, and maybe work out what the next page people go to, and work out the probability distribution for that. You could do various things, and then you might want to start doing some hypothesis tests on that. And whenever you start needing to do that, then you start need to do standardization to be able to try to do some further analysis for it. And so some of these skills here, sort of a foundation for some of that more advanced sort of stuff. It's roughly the idea. But anyway, so that's a simple probability distribution. We sometimes, though, want to consider more complicated ones where we have not just one variable, but we have 2 interacting variables. So we have 2 variables that sort of interact with each other. So this is an example, and I've just made them. I've just got them completely made up at this point in time. As I said, in real life, you can generate these by just observing stuff. So you just, so you can just go and watch, or you can count, and then you can do it. The problem with that is that the probabilities tend not to be very nice. They tend to be non-recurring decimal. So I made it up just to make it look pretty, essentially, easy to deal with. But the mechanics of dealing with them is exactly the same, which is good. So here we've got 2 variables. X can be 1, 2, 3, 4. Y can be minus 2, 0, and 1. So these probabilities here are called the joint probabilities. So this 0.1 here, for example, would be the probability of getting X is 3 and Y is 0 at the same time. So things we might want to ask then is, what's the probability of just getting X equals 1? And that would be this value here. And the way to do that is by adding in the numbers up. So how about I'll write down the values for the totals for X's. Can you just type the totals, so the 3 different numbers here, that would be the totals for the Y's, for the marginal probabilities. Yep. So adding up, you're getting 0.4, 3.3. And you can check if you got the answers right or not. If you add up all these three totals, you should get 1. Because for it to really work properly, adding up all these numbers should happen definitely. So if it's over 1, roll. If it's under 1, there's things missing. And so you're really looking for a total probability of 1. That covers everything. Now you can try to approach this using the concrete fashion before. So you can go, let's assume I've got 10 different numbers, and so 10 different measurements, and see what sort of things happen. And we could do that sort of approach, or we could try to do it directly. So I will, just for the first B, C, D, E, I'll just try to do it the direct approach. But if you need to, I'll try to do it the more concrete approach. I'll do the more concrete approach just for the bottom one, because that's the one that tempo really stretches your brain. So it's good just to see a bit more concrete, perhaps. So B says, what's the probability X is greater than 2? Well, this doesn't really care. This question doesn't really care what the Y values are. And so the Y values can be anything at all. So therefore, we only have to look at just these probabilities down the bottom, which just tell you just about the X values only. It doesn't tell you the interaction at all. And we can see that those two cells correspond to X is greater than 2. And so the total probability then would be just the summing of those two cells. So what's the answer? So probably X equals 3 would be this number here. That's 0.2. Probably X equals 4 is that number there, 0.5. So add them together, you get 0.7. Now, common errors, so certainly when I saw it in my internal class, people forget the difference between greater than and greater or equal to. So they are different. They certainly give you different answers here. And you've got to make sure you're really clear which of the two it is. And that's true for lots of other things. So, and it gets even harder when it's in English. So the first one in English, say greater or more. The greater or equal to would be words like at least. That's how you might phrase the greater or equal to, for example. And so English is pretty flexible, partly because English is a mishmash of other languages, really. And so you have multiple ways of describing things. So anyway, so the workout probably of just one variable by itself really is just looking at the margins. That's called a marginal probability. To work out the probability of two things happening at the same time really just requires looking at just the values inside the table only. They're called the joint ones. And the ones that people find most confusing are the conditional probabilities. So let's have a look at this one here. So what's the probability X is greater than 2 given, and that vertical line means given Y is greater than minus 1. So given Y is greater than minus 1 means we are either a 0 or 2. So that means one of those 8 cells there. So one of those 8 cells. And so if we add up all those numbers, that would be the total area we're looking at. And it's pretty easy to work out what the total is because you've already done part of it already. So you worked out the first row was, the second row was 0.3, and the third row was also 0.3. So therefore the total area we're looking at is just 0.6. And so like probability is the number of ways of seeing of this particular event divided by total number of ways we want to consider. And we're only looking at the 0.6. That's our total in this situation. Then what I want to do is I want to look at all of that area which also satisfy X greater than 2. So X greater than 2 would be all of those cells just right there. So they're those four cells which satisfy both x greater than 1, sorry, both y greater than minus 1 and x greater than 2 satisfies both at the same time. And so if I add up those four cells, so 0.1 plus 0.1 plus 0.2 plus 0, um, gives me 0.4 on the top over 0.6, which you can write down as, say, 2/3 more simply, which you can write as a fraction. So you can write as a, which is about 66.7%, for example, writing as percentage, etc. So just like with conditional probabilities, we're just focusing on just the bunch of cells that satisfy a condition. Add up, that would be our total, and then we look at the ones that satisfy both conditions, and that would be the top of the fraction. And it's the same sort of approach that we did for the earlier example, for that matter. Okay. Let's try rubbing out this bit I've done in the middle. Next one here is, what's the probability that x plus y is greater than 2? And the way to do this really is just to think about all the different cells which satisfy this condition. This is both of them interacting essentially. And you're going, well, if y is minus 2, can you have, so 1 minus 2 is negative, that throws that out. 2 minus 2 is 0, no, 3 minus 2 doesn't work. 4 minus 2 is 2, but even that doesn't work. So none of the top row really satisfies this condition. But you get start from the second row. So 0 is 1, no. 0 plus 2, no. But 0 plus 3 does give you 3. So 3 plus 0 gives you 3. That's starting to be in this condition. And 0 plus 4 would also work. And in the bottom row, 2 plus 1, 2, 3, or 4, all of those satisfy x plus y greater than 2. So basically, all of these cells here that I've boxed would satisfy the criteria x plus y greater than 2. And so our probability then would be summing up all those different cells. So if you add up all those numbers, what do you get? Yep, 0.6. And because of the two zeros here, it's just easy done by adding these two things up to the top. And so that's really just looking at all the possible cases. And again, you can try to group things together to make it easier to count if you wanted to. In this case, there's not that many of them, so it's just easy to do it sort of a brute force approach. Okay, so the harder ones here are looking at the averages. That's what normally people get stuck with. So this first one here is, what's the average of x plus y? And you could do it directly, so you can consider all the different values x plus y can be. So it can be -1 all the way up to 6, so there's some values in between. And work out the probability of each of them using the same idea as D, and using that basic formula to work out the expected value of something. You just sum over all the different values of the value we want times by the probability of getting it. That's pretty much the basic idea. But there's lots of options. So a trick for this one here is that the average is just about adding numbers then dividing by a total. And so we could write down E's rather than P's would be a good start. We could, add them up separately and it would still work. And so a trick is, when you've got an average of a sum, you can just do the sum of the averages. That works quite nicely. And that's because average is what's called a linear operator. It's a very fancy way of saying it. And so that things like multiplying by a constant or adding things can be done. You can just take them out of this average operator. Other things like products don't work the same way. So the average value of x times y is not the same as the product of ex and ey. So that happens and only very, very special cases. So that, but it does, but for some, heaps nicer. And so to work out the average of X and Y, really just boils down to the same thing. So how would I do one of them, and I'll let you do the other one. So I'll do EX, and I'll let you go EY in a second. So to work out the average value for, so I have to move over the side here. EX, it's really just for every X value, so 1 and 2 and 3 and 4. So for every value, I want to multiply that by the probability of getting it. So for X equals 1, the probability of getting is 0.1. For X equals 2, the probability of getting that is 0.2. For 3, the probability of getting it is 0.2 as well. And for X equals 4, the probability of getting that is this number, which you can't quite read anymore, maybe 0.5. And we want to add up, then once we get all these products, we're going to add them all up to get our answer. So the bottom's 2, 2.6, 3, so 3.1 I think it is. I also make a mistake, which is quite possible. So that would be the first one, 3.1. Then you have to do the same sort of approach for the average value of Y. Do you think you can do that now? Okay. So same sort of approach. You get minus 0.1, minus 2. Thank you very much. So if you add up these two things, you then get 2.9 as the average value for both of them put together, essentially. And that's the best way. So thank you very much. So this last one is this average value on a condition. So this is an average of a condition. So let's clear a lot of space around. So let's go back to the concrete way of doing it. So essentially, we want to work out the average value we'd get for X given Y is 0. So let's suppose that we had 10 numbers again. It's just the 10. How many would we get for each of them? Well, basically, you just multiply the probability by 10, will give you how many numbers there are. So that'd be no here, none here, 1 here, 1, etc. And then if you do the totals, for example, I do 0 plus 0 plus 1 plus 2, I'd get 3 numbers. So out of my 10 numbers, 3 of them would be Y equals 0. So let's just 2 here, for example. Out of my 10 numbers, 2 of them would have X equals 4 and Y is 0. And so in total, there'd be 3 of them. Out of my 10 numbers, 3 of them would have Y equals 0, for example. So we want to work out an average. And you're going, well, I want to work out I want the average of all the numbers where Y is 0. And work out the average of the X values. Well, when Y is 0, that really just corresponds to just that particular row. And you can see here I've got no number. So I never get X equals 1. I never get X equals 2, but I've got one number here, 1, 3. So one time I get an X equals 3, and I get 4 twice. So essentially I've only got 3 different numbers to pick from. They are 3, 4, and 4. So the way to work out the average would be add up these numbers and divide by how many there are. And so add up the number, you get 11 over 3 would be the answer. And that's the concrete approach. How do we work that out directly without having to come up with the concrete numbers? And certainly we want to be able to try to handle it more generically. So let's just see what the pattern um, is. It's the same idea as before. So an average of anything is equal to summing all the values times by the probability. So the values of x are 1, 2, 3, and 4, like they were before. And this time we have to multiply by the corresponding probabilities. So we want the probability that x is 1 and x equals 3 and 2 and whatnot. But we don't just want the value for x is 1, 2, 3, 4. We want them all on the condition that y is 0. Because we're insisting that y is 0, that will change the probabilities. And we want to add them up. So really expectations are the same idea. It's just the numbers times by probability, take products, add them up. The difference here is because of this condition, we have to add that condition when we work out probabilities. And then we just have to work out these conditional probabilities. And the way to work them all out, like I did before, is to say, look, when y is 0, it means I'm in that row. That happens only 0.3 of the time. So, for example, the probability that x equals 4 given y is 0, well, the total number of ways it happens is 0.3, and x equals 4 happens 0.2 of that. And so this probability here would end up being just 2/3. So if you start doing the arithmetic, the probability x equals 1, it ended up being 1 times by 0 on 0.3, which gives you nothing. Next one is 2 times by, again, another 0 on 0.3. Again, nothing. Next one is 3 times by, finally getting something, 0.1 on 0.3. And the last one is 4, lots of, as I just said, this number over here, 0.2 on 0.3. And if you work at all that, then you get the same answer of 11/3. And just to see how things match up, the 3 times by 0.1 and 0.3 really is the 3 and 3. They match up. And the 4 times by 2/3, so the 4 times by 2/3 really is the 2 4s on the top over the 3. And so the 2 4s would be the 2 4s on the top, 0.3 corresponds to 3 on the bottom. So the concrete and the more robust way should do match up, of course. But often people get having hard to understand what it's trying to work out. So, and as a recap, this is the average values we have for x's when we know that the y value is 0. And we found out the answer was 11/3, which is 3 2/3, or 3.67, say, to 2 decimal places. And so those questions there, the two I've done, are the ones most similar to your online assignment. And so hopefully that helpful for those. But I do want to consider other sort of distributions as well. So although these next questions don't apply so much for your assignment, they are good. So hint, hint, might be useful to do some of these for your exam. Okay. So we'll have a go at talking through some of these. I won't do them all explicitly. So question 2. So you've got a clay pigeon shooter. So there's someone won. So a female won a gold medal in the Olympics for clay pigeon shooting. It was about a week and a half ago. So they hit the this clay pigeon, so just a rubber red disc, with probability of 0.8. So she's about to go to a shoot that has 10 of these clay pigeons, and she's pretty good, so therefore they're independent. All the shots are independent of each other. So a real person a not so good person like me, if I miss the first 9, then my mind would be completely wasted, and I'm pretty confident. I'm pretty sure I'd miss the 10th one because I've lost all my confidence. A good person would just always see as a new clay pigeon every single time. So you got to justify to yourself that the number. Let's consider the number of hits that you make from 10. We'll call it X. So it's a number between 0 and 10, and it's going to be random because it depends on what she does. You had to try to justify its binomial. So, do you know anything about binomial, Dylan? And can you explain in any terms at all why it's binomial? So, in an exam sort of situation, I probably wouldn't ask that question, but I might ask the same sort of question in the exam, just with that removed, essentially. Just with part A removed. So why I've put it in here is because I could easily ask a question in something like an exam or an assessment item where the word binomial is not mentioned, but you have to realize that it corresponds to something binomial. And so thinking through ways of recognizing it's binomial is important. So that's all I'm really looking for. What ways do you recognize, oh, that's just binomial? So see what you say, and I'll tell you some other ways you might recognize it's binomial. Yep. So binomial literally means two names, and so normally the obvious way to notice binomial is when you have two outcomes, just like you say. So, and she hits it or she doesn't hit it. So that's normally the best way of spotting it, which is awesome. There are some other things that need to work out though, and that is there needs to be a fixed. So there needs to be a fixed number of trials, and so in this case she's clearly trying to shoot at 10. So, and there needs to be a clear upper limit for what there is. So the other distribution that I'll mention, I mentioned in lectures, is the Poisson distribution, or looks like poison with a double S essentially. It's how you look right in English. So it's French for fish. I don't know. My French is terrible, but my understanding is that it's pronounced more like poisson or something like that. But if you're a real French speaker, you probably can tell me exactly how to pronounce it. I'm trying to do justice to the guy's name. I'm probably failing badly, unfortunately. So with Poisson is also counting the number of successes, essentially, number of times things happen. But with a Poisson, you're counting over a time period or something like that, and there is not normally two outcomes. So you can either get not happening or happening once or twice or 3 times. So in that sense, there isn't those two clear outcomes, which is why what you've written there is a good way of detecting binomials. That's 2A. It's a simple one. Let's just do 2B. We'll talk broadly how to do it. I won't get all the answers. So calculate the probability she hits 8 or more clay pigeons. So that's pretty much saying what's the probability that the number of times you hit something is 8 or more. And so 8 or more, really, first thing you have to work out is that's greater than or equal to 8. And depends how good your English skills are. So if your English is a second language, for example, sometimes they're a bit harder. And so maybe if you need to, just writing down what some of these things mean. So 8 or more is just greater or equal to that number. So how do you do this? Well, you're allowed a formula sheet in the exam, and so I would strongly recommend you write down the formula that for binomial, for a binomial, the probability that a random variable is equal to some value, so 3, 7, 8, whatever it might be, is equal to the number of ways of choosing those X things from how many trials there are, times by the probability of getting a success for one of these goes, to the number of successes you want, and then the probability of missing times by the number of misses you want. Now, just as a note, I did an example formula sheet. In the example formula sheet, I stuffed that 1 minus p out, which I wrote the other day, which I have now corrected and uploaded. But if you have printed out the formula sheet earlier, then there was a slight mistake in that formula. So I should just make that really clear, because I want to make sure I write the right one. So that's the formula. So in order to use this formula, you need to know what the possible X values are, which already depends on the question. You also need to know what N and P are. So what's N in this situation? Yeah, so N's the total number, and which in this case is 10. That's right, absolutely. And what's P? Pardon me. Yep, so P is the probability of getting a success for just the one trial, which in this case is 0.8. Absolutely. So you need to know those sort of things. So when you work at probability of X is greater than or equal to 8, you notice the formula only really handles equal signs. That's all it has. So in order to use these formulas, you really need to break these things down into lots of equal cases. And you're thinking, okay, well, what values are greater than or equal to 8? Well, I can do the first one. X equals 8 is the first case. But there are other ones as well. So another value that's greater than or equal to 8 would be 9. And then you'd have 10 as well. And that's when you stop. And the reason why I can stop there is because there are only 10 shots she's having a go at. And so she can't get any more than 10 clay pigeons because that's all there is. And so to work out any greater or less than that sort of thing really is to split down all the different cases. And what we need to do is for each of these cases, so 1, 2, and 3 cases, we will need to use this formula. So I'll do it just for one of them. So I'll do X equals 10, just the last one. Why I do that one is because I've got a chance of doing it. I've got to simplify it a bit, so I've got a chance of writing down the answer easier. So X equals 10, I've got N is 10. So for my my 10 trials, I'd like to choose all 10 of them to be successful. And then I want to put I would like the probability of succeeding one trial is 0.8. And I want to put that to the power of the number of successes I want. So I want all 10 to be successful. And then I'll multiply that by the probability of a failure, which is 1 minus 0.8. And I want to put that to the power of the number of failures I want. So the number of failures would be total number of trials minus the number of successes. Now on your calculator, if you have to type into these things in your calculator, I would do 10 minus 10 in my head to get 0, just make it a bit easier. So I'll write this as 10, choose 10, times by 0.8 to the power of 10, times by, and you can use brackets in your calculator. So if you have to use brackets, you have to put brackets for the power 2 probably. It does depend on your model. But I would be tempted to write some of these things on a piece of paper first. So 1 minus 0.8 is 0.2, 10 minus 10 is 0. And certainly the powers, I'll be very keen to simplify just to make it easy to type in your calculator. And then you can point that out. So, and you're getting 0.11, say, to 2 decimal places. By doing all that. So, and you can do the other ones too. So you'd have to do the other as well to get the answer. So just we'll finish off with C. How do you say what's the probability that x is 7 or less, which ends up being 7 less than or equal to 7. And you go, well, I could do the same sort of approach. That means x has got to be 0 or 1 or 2 or etc. up to 7. And as soon as I'm having to really put ellipses down just to make it easier to write down, it suggests to me that's probably going to be a rather long way of doing it. So I could split it up into 8 cases, and for each of those 8 cases, use this formula. It doesn't sound like a very fun way of doing it. Can you think of a better, a different way, a quicker way? I'll call it a quicker way of doing it. And the direct approach works, and indeed, if you ask the computer, the computer would do it exactly that direct approach, quite quickly for that matter. But as humans, we often like to try to get quicker methods. Any ideas? No, you can use the Poisson distribution to approximate binomials if you've got a large number of trials. So if n here, if n's really big, you can use a Poisson distribution, but 10's not very big, so you can't really use it here. So it is binomial, but the trick you can do all the time, and the basic rule is if you've got any event, you can often think of the opposite. So the opposite event would be just a bar on the top. So the probability of getting an event is 1 minus the probability of not getting it. So in this case, the probability of getting x less than 7 will be 1 minus the probability of not getting less than or equal to 7. So what's the opposite? So if you don't get less than or equal to 7, what do you get? How would you describe what the opposite would be to this thing here? And it's an indirect method because you're trying to do it from the opposite point of view. But as we've seen by proof by contradictions, for example, this idea of doing things opposite is a common one in maths and useful. Yep, and so it's x is greater than 7. That's correct. And just to make it really obvious, x is greater than 7. It corresponds to, if it's just integers at least, which they are, would be greater or equal to 8. And if you then start looking, hold on a sec, if I'd done all the calculations, that would be the answer to the previous part. And so you could do this one, part C, just by doing 1 minus the answer for part B, which is much more straightforward than trying to use this formula 8 times. So I look for the alternative ways. And this idea of considering the opposite case is useful, and you can certainly use that idea in some of your questions in assignment 2. And not just the distribution part, might be some of the earlier ones. And you can do that similar concept even in counting, not just even in probability as well, if you wanted to. So I'll finish it there today, unless you've got any other questions. But just recapping, so the things that I really wanted to focus on was looking at probability distributions. So just the general distribution sort of scenario, how you work out things like averages, variances, standard deviation, that sort of thing from it. And then looking at just one special case of binomial. The other special case, Poisson, is also important. It's similar, except it has a different formula to use. So you really have to split up in cases like this one, but use a different formula. It sort of is oversimplifying, perhaps. And the key, really important, is to be able to distinguish between the two of them. So binomial is counting where each trial, so to speak, is just one option, either yes or no, and there's clear upper limit. So there's clearly only 10 clay pigeons this girl could ever shoot. For Poisson, there is no clear upper limit. That's a good way of distinguishing it. But anyway, thanks for that. All the best with finishing off online assignment 2. If you have any questions, I'm around. So we're having a break from these classes for 2 weeks. I'm having, I think, 1 day leave, so I'm around lots of the time, so you can always speak to me on the phone or via email, etc. If you've got any questions, that's not a problem. And I encourage everyone to keep working. So someone submitted assignment 3 yesterday, so well done to that person. So I encourage you all just to, if you're still a distance student, maybe you can use this time to either catch up on stuff or maybe shoot ahead, depending what else you need to do. So it does depend. D is pretty important about being flexible, so use that opportunity. But anyway, thank you very much for coming live or watching the recording afterwards if you get to that stage. So thanks.